We've got ourselves coupled first order simultaneous differential equations here. So scientists are studying the effect of introducing a population of type A bacteria, and the number of these is going to be X, into a population of type B bacteria where the number is Y. And this is all dependent on T days. Okay, so we've got these two equations and we're asked to combine them essentially to get a second order differential equation for X in terms of time. So what I'm going to do is take this one here and differentiate it with respect to time. This will give me d2x by dt squared equals dx by dt plus dy by dt. Right, now I need to get, I need to replace dy by dt and to get x in there. So what I can do is write it as dx by dt plus 3y minus 2x. Just use this. Okay, but now I need to get rid of the y. That's the last little bit. But what we can then do is go back to this one here and write that y is equal to dx by dt minus x. So I will get dx by dt plus 3 lots of dx by dt minus x minus 2x. And this will end up being 4 dx by dt. And then I've got 3 times minus x minus 2x and minus 5x. And remember, that is my d2x by dt squared. And all we need to do now is rearrange it and get to here. So I'm not going to write it down. But that's what you would write down. Good. Now I have to determine a general solution for the number of type A bacteria at time t days. Got to solve this. And we can construct an auxiliary equation. K squared minus 4k plus 5 equal to 0. Let me show you where that comes from. So we're going to try letting x equal a e to the kt. Then when we differentiate, you just basically bring the k down. If you differentiate twice, you do it twice. We're going to get k squared a e to the kt minus 4k a e to the kt plus 5a e to the kt equals 0. You can cancel out the a's and cancel out the e to the kt's, and you're left with this, our auxiliary equation. So if we can solve now for k, then we can sub it in. Although we're not in this case, and you have to be a bit careful because it's gonna be complex. So we could just put it into the quadratic formula, to be honest, or you could complete the square. But we get that k is equal to 2 plus or minus I. And what that then means is that we've got a e to the 2t, and instead of writing e to the minus it in there, we can replace it with a cos. It becomes cos t. And then you get b e to the 2t sine t. That is our general solution. Remember, there's two, although we've tried this, now we've got two different values of a, we can just do a linear combination of them. Let me show you where that comes from. Okay, it is something to learn, but it's also important to see where it comes from. So if you go back to our original trial, now that we've got k is 2 plus or minus I, we could say that x is equal to, I'm not going to use a here, let's call it c, e to the 2 plus I times t plus d e to the 2 minus I times t. And this is a valid solution. It's just we want to write it in using, so it's all real, basically, because these would be complex, sorry. Now I could write it as c e to the 2t e to the it plus d e to the 2t e to the minus it. And now I'm going to use Euler's relation. This here is going to be cos t plus I sine t. And this here is going to be cos of minus t, which is just cos of t, plus I sine of minus t, which becomes minus I sine t. Then I can bring the cos terms together. I'm going to get because I've got c e to the 2t cos t plus d e to the 2t cos t. It's going to be c plus d e to the 2t cos t. And you can see it taking form. It looks like this now. And then I'm also going to get c e to the 2t I sine t, and then minus d e to the 2t sine t. So there's minus d here, e to the 2t sine t. And essentially at this point, I can just say that this here is going to be defined to be A, and this here is going to, oh no, sorry, not that. This here is going to be defined to be B, and I will get the solution I had before. So that's where it comes from. You could just go straight to it using the imaginary part, but I just wanted to talk about that. Right, in C, we're asked to determine a general solution for the number of type B bacteria at time t days. So they want us to work out what y is equal to. And for this, I'm going to use the dx by dt equals x plus y. So y is going to be dx by dt minus x. So I'm going to need to differentiate my answer from part B. I'm going to get 2a, I'm going to need to be using the product rule here. So 2a e to the 2t cos t. That's when I differentiate e to the 2t, keep cos t the same. Then I'll get minus a e to the 2t sine t. And we'll do similar with the other one. I'll get plus 2b e to the 2t sine t plus b e to the 2t cos t. And then I'm minusing a e to the 2t cos t and minusing b e to the 2t sine t. And let's again bring all the cos terms together and all the sine terms together. So if I just factorize out e to the 2t cos t for the moment, I will get 2a from this one. I'll get a plus b from this one and a minus a from this one. Then I'll have plus e to the 2t sine t, do similar here. I'll get a minus a plus 2b, then minus b. So this is then going to give a plus b e to the 2t cos t plus b minus a e to the 2t sine t. You could factorize the e to the 2t out, of course. I think it's pretty good to leave like that. Now, the model predicts that at time, capital T hours, the number of bacteria in the two populations will be equal, and then we're given initial conditions. And we're asked to determine the value of capital T. So the initial conditions are going to help us work out what A and B are. So I just want to collect things together. All right, here's my Y. And I've also got my X up here. So T equals 0. Let's put it into X. We're going to get 100 equals A. E to the 0 is just 1. Cos 0 is also 1. And then sine 0 is 0. So actually, we just worked out what A is. And then 275 sub nt equals 0 into here. I'm going to get A plus B. which means b is going to be 175. So I can write down my new x. X is going to be 100 e to the 2t cos t plus 175 e to the 2t sine t. And y is going to be, well, I add them together, I'm going to get 275 e to the 2t cos t. And then b minus a is going to be 75 e to the 2t sine t. And remember, we're looking now for the time at which the two are equal. So 100 e to the 2 capital T cos t plus 175 e to the 2 to, sorry, that should have been a capital T as well. Okay, that is going to equal 275 e to the 2t cos t plus 75 e to the 2t sine t. What we can do is cancel out the e to the 2t's. Now I'm going to collect together my cos terms and my sine terms. I'm going to get 100 sine t by minusing 75 sine t from both sides. That's going to equal 175 cos t. Again, this is perfectly set up now to get, in terms of tan, we're going to divide through by cos, divide through by 100. Tan t is going to equal 175 over 100. That ends up being 1.75. Let's do inverse tan. Remember, we're working in radians. You get 1.0516. Now, you've got to be a bit careful here because it says at time t hours, and this is in days. So don't be called out. We've done all the hard work. It's times through by 24, and this gives 25.2 hours. Brilliant. So it's got to be said, there's a lot of ways you can not get that answer 25.2. If you made a little mistake with any of your general solutions, and then with your particular solutions, and then of course you have to solve a trig equation, get the number of days, and remember to times through by 24. Now for the very last question, it asks us to suggest a limitation of the model. So I've got to say I did not get the mark for this, because I looked at x and I just said to myself, as time approaches infinity, x is going to approach infinity, and I thought that's enough, but that was considered a rote answer. I mean, I still don't really get it. I can see that it's going to go to infinity. That is clearly a limitation. But what they were looking for, and they say that this is the worst answered question in the paper, is that, yeah, if you just wrote about it tending to infinity with no indication of investigation of what happened. So, okay, would I get the mark if I talk about e to the 2t going to infinity? I mean, I just looked at it and I know that it does, and it doesn't. I know that cos t and sine t are oscillating, but it's not really going to matter. T is like a billion, and like there's going to be a part of the cycle where this is, we know that at some point cos t and sine t have the same value. So yeah, that it's definitely going to approach infinity. Maybe if I'd said that in more detail, I would have been okay. So what they were actually looking for was about them becoming negative. So because cos t and sine t are oscillating, there will be periods where they'll be negative. I'm still not happy with this. It seems like guess what's in my head kind of question. We want you to say that it's going to become negative, and that's going to be the answer. And you don't need to go into details on that, but if you say that it approaches infinity, then no, that's not allowed, unless you go into like some sort of detailed analysis and explaining why. Anyway, I wouldn't stress about this, but I suppose, yeah, I don't know. I suppose just think about flaws in the model. Both of them are there, in my opinion. The fact that x approaches infinity, y approaches infinity. I mean, it is oscillating, to be fair, but also, yeah, that it becomes negative. Anyway, well done with this question. Still not happy with it like that.